Three-phase Y, the basics, voltage, current, and some calculations. When we're dealing with three-phase systems, it's important to understand that there are additional terms that we use when referencing voltage and current. Now, these terms that we use will be the same for both a Y system and a delta system. However, their values will differ between the two configurations. When we're dealing with a Y system, the following are standard rules. What we have is three individual single phases. These single phases have both a current and a voltage. We're looking at a source right now, which means that there are three individual windings on the alternator that are separated by 120 degrees. As the alternator spins, it generates an individual voltage. And we can see here that if we measure between two of the line conductors, we will get a line voltage also. So there is a phase current and a phase voltage. There is also a line voltage and a line current. In a Y system, we can start to make some pretty significant assumptions. First off, each of the phase voltages will be identical, and they're usually referenced with 2 points on the phasor. So voltage AN from this point to the neutral or the common point. BN, CN. Now, if all the phase voltages are identical, this means that all of the line voltages will also be identical. However, the line voltages will not be the same value as the phase voltages. And this is where the relationship of √3 comes in. If we take a look at the calculation for the voltages in a Y-connected configuration, the line voltage is equal to the phase voltage multiplied by √3. And of course, if you wanted to reverse the equation, you could say the phase voltage is equal to the line voltage divided by √3. Now, some of the common three-phase Y voltages that we have are 120/208, which is pretty common across all of North America, 277/480, which is most common in the US, and 347/600, which is most common in Canada. If we take a look at a phasor representation of a three-phase Y system, we will see that voltage or phase voltage AN is always drawn on the reference phasor or reference line, meaning it's always at 0 degrees. Voltage BN is then going to be 240 degrees because of the rotation effect that we have on a typical phasor diagram. It happens second, and then third would be CN at 120. Regardless of the loads that are connected, these voltages will remain constant. And so there's never any further investigation required as to how will they change or where will they be in this situation. They will always be in this set location because we work with standard constant voltage three-phase sources. What you should notice is that the line values are longer, thereby representing a larger voltage, and the line values will lead the phase value by 30 degrees. So voltage AN at 30 degrees, voltage BC at 270 degrees, and finally voltage CA at 150 degrees. Again, these are standard locations that will never vary. If we were to look at the currents of a three-phase system, they're fairly straightforward, and that is due to the phase current being in series with the line current. Now, when we look at a delta system, this will change a little bit. So for Y, simply be aware that phase current is equal to line current. Well, with all of that, let's do a few examples and see if we can't align some logic with some of these rules that we have learned. The first example is here. We've got a three-phase connected or configured load, and we have a three-phase source connected. We see that the source is a 347/600 volt source, and that means that the line-to-line voltage is 600 volts. If it's 600 volts here, and they're connected in a Y configuration, that means that the phase voltage must be √3 less. That would mean that if I took my 600 and divided it by √3, I should end up with 347 volts. Let's take a look at another example. Again, three-phase source, we have 277 volts now across the load. And it's significant because it's one phase of my three-phase load. Now remember, if we want to know the line value, we need to utilize our knowledge of phase and line values in a three-phase system. The line voltage should be √3 larger than the phase voltage, meaning we should take this and multiply it by √3. Now, if you're unaware, on your calculator, you're going to have a square root symbol, and it really depends on the calculator. Mine is right here, and it actually has to be used by clicking the second function button first, and then the x squared button. And then we get that square root symbol. All I then enter is the number 3. There's my square root 3. And we want to, in this case, multiply it by the phase voltage times 277. That gives me 479.7, which more commonly on a nominal system voltage scale would be 480 volts. This would then mean that the source that we are connected to is a 277 480 volt three-phase source. Let's take a look at this one. What is the load current that is flowing through each one of my individual phases? Now we can calculate both the line and the phase current because they are in series. I'm connected to a 120 208 volt source. The line voltage is 280 or 208 rather, which means that each of my 15 ohm loads must have √3 smaller, meaning 120 volts must be across each one of those individual loads. Now, if I want to calculate the individual current of a single phase, all I need is a basic single phase equation, which we see right here. The voltage divided by the ohms. So 120 divided by 15, which gives me a grand total of 8 amps. Now remember, if it's 8 amps flowing through the individual phase, it must also be 8 amps that is flowing through the line connection. So in a Y system, we say that yes, the line and the phase value are identical, in this case, 8 amps apiece. What about this one? Example number 4, what are the load ohms? Well, again, remember, we are looking at phase voltage and Ohm's law. So for 18 amps worth of current, we probably need to know what the voltage is across each one of the individual resistive loads. If it's 208 volts from here to here, it must then mean that we have 120 volts from here to here. Now, if I want to know the ohms is going to be equal to the voltage divided by the current. So E over I, which is our basic Ohm's law formula. In this case, the voltage is 120 volts. 120 divided by 18 gives me a resistance of 6.66 ohms. And since each one of the lines has the same voltage, so 208 and thereby 120 across each one of the phases, and the current value is the same, that would mean that the ohmic value for each of our individual phased loads should be identical at a value of 6.66 ohms. Well, let's take a look at an example that sort of includes the full source and the full load. Example number 5 has this, and I've written down some of the rules that we have for our three-phase Y systems just so we can keep it clear. Now, the process that we need to go through in order to answer questions like this is to first determine what the source voltage is. If we know the source voltage, we can then apply it to the load. But if we don't know what those voltages are, we really can't get anywhere. So let's look at this first example, 120 volt phase. That's the only information that's given to me. And then over here on the load, they've told me that they're 5 ohms each. Well, for me to be able to do anything of use with this question, I need to first determine that if the phase voltage is 120, it means that the line voltage for this source must be 208 volts. If it's 208 volts line to line, it must then mean that the phase value over on my Y connected loads must be, again, a 120 volt magnitude. Now I'm only going to sketch it in here one place with the understanding that each of the individual 5 ohm loads will have also 120 volts. Now we're going to look at what the voltage value is then across each of the individual items and the current value. I want to know how many volts across each one of the loads, 120 volts. What is the line voltage for all of my conductors? Well, that would be 208, 208, and 208. And finally, what is the current that is flowing through the phase and the line of this circuit? Well, the current value I can calculate by simply using Ohm's law. Remember, 120 volts divided by 5 ohms gives me 24 amps. That means that yes, IB and IC, the line current values, will all be identical. And as you have already figured out, the phase voltage across my load for each of the individual phases is identical at 120, and the line value for each of the 3 individual line possibilities is 208. Let's take a look at another example. This one is almost identical. However, we're using a different voltage. This one is 347 volt phase, which means the line value must be √3 larger. Again, we're going to work out what the phase voltage is across each one of my loads, the line voltage across each line conductor, and what the line current is that comes from my individual loads. So if we look at the line voltage, it must be √3 larger than the phase voltage coming from the source, meaning I have 600 volts. If I have 600 volt line, it means that across each one of my individual phases, I must have √3 smaller, which is 347. As I've done in all of the other instances, I'm not going to draw it in for each one of the phases because I already know they're identical. The only step left for us to accomplish is then to determine how much current is going to be flowing on the line conductors for each one of my connections to my load. That's simply Ohm's law. Current is equal to the voltage divided by the ohms. And people will often ask, well, is it going to be the line voltage we use or the phase voltage? And I say to you, if all we want to know is the current that's flowing through this section here of that resistor, then all we're using is the voltage available across that object, which of course is the phase voltage. So the current value we get is 34.7 amps on each of the line conductors, 347 volt phase value for each of the phases, and 600 for each of the line connected conductors. Now there is a little bit of a difference between something referred to as a balanced system and an unbalanced system. Up to this point, we've been looking at examples that had no neutral conductor. Now that's because these were balanced, and that simply meant that each phase had an identical ohmic and power factor type of single phase load. So 5 ohm, 5 ohm, 5 ohm, all resistors. The current in A should equal the current in B, should equal the current in C. And due to that, there's no unbalanced value of current that would necessitate a neutral conductor. An unbalanced connection or configuration, however, where we have different ohmic values and or different power factors, will have an unbalanced value of current that a neutral conductor will be required to carry. The way that we will then calculate the neutral current is through vectorial addition, which is something that we have done in second level in order to add together individual phases of a circuit. This and the procedure for how we do this will be covered in the next presentation.